Great. Thank you. Thanks a lot for having me here. I'm really excited to be here in this amazing venue. A lot of today has been about synthetic data, and I'm going to continue that trend. I'm going to tell you a little bit about how we train models using kind of low fidelity, low cost synthetic data that work in the real world. Since we've been talking about this a lot today, I won't dwell too much on why this is important. But if you look at the success stories so far of deep learning, one thing that they have in common is that they require millions or even tens of millions of labeled examples. And so for those of us in industries like robotics where labeled data is expensive, this presents a problem. And synthetic data is one potential solution to that problem. So if synthetic data works, just by synthetic data, what I mean is low fidelity simulated versions of the real data set that you want to be able to model. So it could be from a physics simulator or a graphics engine or something like that. And if synthetic data works, then there are a bunch of kind of really compelling advantages over real data. So since you're generating the data as opposed to collecting it or acquiring it, you can run it on your entire data center, which means that it's cheap, it's fast, and it's scalable. And since you design the world that the data comes from, it's easy to label. And so, we work in robotics, among other things, at OpenAI. And robotics is one area where real data is particularly hard to come by and particularly hard to label. And so one of our core research focuses has been how to make synthetic data work for challenging robotic perception and manipulation problems. And our approach towards synthetic data started with a belief. And the belief was that rather than investing in making our simulators more and more realistic, which has diminishing returns, instead we wanted to invest in increasing the variability of the simulator and making them more and more random. And the first application of this idea was a technique that we call domain randomization. And the idea behind domain randomization is that if you massively randomize all of the non-essential aspects of the simulator, then it forces the model to ignore those non-essential aspects, which will increase its chances of working when it's deployed on a very different data set. One of the first applications that we used this for was for one-shot imitation learning. Looks like the video isn't working, but I'll give a quick description of it. Essentially, we wanted to train a model that could, from a single human demonstration, stack blocks in a particular configuration. And so we built a system that consisted of two modules. The first is a vision module that we trained with domain randomization, and then the second is a control module that actually moved the arm of the robot. And so we trained the model on low fidelity synthetic data that looked like the images on the left, and we tested it on real scenes like those on the right. And we were able to localize the objects in the scene well enough that our control module could pick them up and imitate the human's behavior. Next, we wanted to see if this applies to control as well as perception. And so we built a randomized world that consisted of hundreds of thousands of different counterfactual physics scenarios for this puck sliding task. And so each of these it was different. None of them really accurately modeled the physics of the real world, but we learned on those variable simulations, and what that allowed our model to do was to learn how to adapt to new physics very quickly. And so when we deployed it in the real world, even though it had never been trained on real world physics, it was kind of quickly able to figure out how those physics worked and solve the task. And the last application that I'll talk about is grasping. And so the goal here is, we want a robot that when it sees a new object for the first time, it's able to immediately know how to pick that object up. And this is one of the long-standing problems in robotics. And instead of collecting the objects that we had around the lab, which is normally how grasping training works, instead we procedurally generated millions of these kind of low-quality randomized objects like the ones that you see on the left. And when we trained on those objects, kind of surprisingly, we were able to deploy these models in the real world and pick up real objects successfully, even though the model had never seen real objects during training. It had kind of learned some features of the geometry of objects that allowed it to generalize to them. And so now, so I've talked a little bit about how we've applied domain randomization and synthetic data at OpenAI so far. And now I want to talk a little bit about what I think are the next directions for making domain randomization and synthetic data work better. So I think the important research directions around domain randomization address what I think are the three main limitations of the technique right now. The first is that, in most real-world settings, we do actually have some real data. And we have much more synthetic data, but we have some real data. And so the question is how to incorporate that real data in the most effective way. Another limitation is that it can be challenging to design these large-scale simulated worlds. And so I think another important question to ask is, can we do that automatically? Can we use images of the scene to generate synthetic worlds that can give us more training data? And then the last limitation is that even though synthetic data alone can be used to solve a pretty wide variety of tasks, there's still a gap between the performance in simulation and the performance on the real data. And that gap is like somewhere around 3 or 5x. And so figuring out how to eliminate that gap is, I think, an important direction as well. And if there's a few things I want you to take away from this, it's that synthetic data alone can already solve a lot of pretty challenging tasks in computer vision and beyond. And if you want to use synthetic data to solve your problems, there are two things that I want you to remember. The first is that you might want to consider investing in variability of your simulator as opposed to making your simulator more and more realistic. And the second is just to keep in mind the limitations of the techniques right now in fields where domains are hard to generate in simulation or where you need really, really high precision. Thank you.